to thank the organizers for having me here, but also, of course, for putting together such a nice and well-balanced conference. I really enjoy it, and I think it's perfect. What I'm going to speak about is work in progress within Tenders Munibus from the University of Vienna and Fiona Tortetzka, University of Bristol. And it doesn't give new tensor categories, but it describes a useful application of tensor categories. Okay, so first I want to talk about what are trisection invariants and trisection diagrams and trisections. So trisections are essentially a new way of describing four manifolds. So this was introduced in 2016 by Gay and Kirby. And the idea is that you have an oriented, connected, closed, smooth four manifold, and you have two numbers, k and g. And a GK trisection of this manifold is a decomposition of the four manifold into three four-dimensional handle bodies. So each of them is diffeomorphic to the k-fold connected sum of S1 times the 3-ball. And this diffeomorphism sends the intersection of two subsequent such manifolds to a standard Hegat decomposition of a G minus k-fold stabilization of the standard decomposition of some standard surface. So this looks roughly, if one describes it in terms of a Hegat diagram, this looks like this. So here one has k times this situation. So the Hegat diagram that here you would have like lines in red and blue as usual for the Hegat diagram, and then you would have another part that comes from the stabilization, where the blue and red lines lie as the A and B cycles of the torus. So in terms of Hegat diagrams, this is what it looks like, the intersection of two subsequent ones. Okay, so this sounds pretty abstract, but it can be made very concrete. So first, one should note that every such four manifold has a GK trisection for some some K and G, where K is between 0 and G. And the K and the G are related by the Euler characteristic of the four manifold. So this has been shown by Gay and Kirby. Yeah, and just as Hegat decompositions can be described in terms of Hegat diagrams, the trisections can be described in terms of trisection diagrams. So such a trisection diagram is a surface of genus G, sigma, and it has three sets of G curves each, a red one, a blue one, and a green one, alpha, beta, and gamma. And the condition is that for any two subsequent sets of curves, so alpha and beta, beta and gamma and alpha, this defines a Hegat diagram for this k-fold connected sum of S1 times S2. So it's essentially like a generalization of a Hegat diagram. And there are some examples. So the most important example is this one. So here we have and we have red, blue, and green curves. Yeah, the Hegat diagram condition says, of course, that each of the red, blue, and green curves has to be non-separating, and that each curve can only intersect curves of different color. So it need not intersect, but if it intersects, it may not intersect red, red, or green, green, but only curves of different color. And this is one of the simplest trisection diagrams. This is for S4. And here one can see that k is equal to 1. So we select two colors, for example, red and blue. And k is essentially the number of double circles, where blue and red are next to each other. And G is 3 here. So that tells us we will have two situations where blue and red intersect like the A and B cycle of the torus. Okay, then there's other simple examples. For example, CP2. There you take as the surface the torus. There we have Euler characteristic is 3, genus is 1, and k is equal to 0. So there are no parallel red and blue circles and so on. Okay, so this is a way of describing four manifolds that is different from the usual triangulations or handle decompositions. And essentially it comes from a Morse 2 function. And it's nice in a way because it gives everything on a rather simple and easy to process structure, namely a surface with some curves of different colors.
If you say manifolds, are these topological manifolds?
They're smooth. So here they're all smooth in the following. Okay. Okay, so one has some control over this. Every manifold admits such a decomposition, such a trisection. Under the conditions I gave on the last slide. Now one asks, of course, do many of these trisections diagrams, do they maybe give the same manifold? And this is, as usual, it's not unique, but one has control over how to relate trisection diagrams that describe essentially the same manifold. So if I have two trisection diagrams of the same manifolds, they're related by a finite sequence of some moves. So the first moves are orientation preserving diffeomorphisms of the surface. The second move are called 2-point moves. They're essentially like colored Reidemeister 2 moves. So Reidemeister 2 moves like a knot theory, but only curves of different color can intersect. So you have them only in this version. The third one are 3-point moves. They're essentially colored Reidemeister 3 moves. And here the condition that only curves of different colors can intersect forces you to use 3 colors. Then the fourth move are handle slides. So here one has 2 red curves, and one takes a small neighborhood of these red curves in the surface and then one connects them by a path that is also thickened a little bit. There may be various green and blue curves intersecting these. And then you are allowed to take one of these red curves and kind of make it approach the other one and then slide it over the other one. So this is a handle slide. And the final move is something that's called the stabilization or destabilization move. It means that you take the connected sum of a trisection diagram with the trisection diagram of S4, which is also called the standard diagram or the stabilization diagram. So this is like a short list of moves. And the idea is then, if you know these moves, then you can define a trisection invariant in roughly the same way that you can define a knot invariant by invariants under moves of knot diagrams. So you can say a trisection invariant is simply a map from the set of trisection diagrams to the complex numbers that is invariant under the moves M1 to M5. And that means if you have a trisection invariant, then you have an invariant of smooth-oriented connected 4 manifolds. Yes?
Perhaps related to Christoph's question, is it possible to say if you like further moves that would identify? Not sure.
So I do not know this. So the work I gave Fabi was in the smooth framework, and all the subsequent work on this was also in this. So I have no idea if this can be applied to topological or if you can make a more economical version. Simply unknown.
Do you know if it's known whether moves or manifolds can be told apart by this invariance, even if they are homeomorphic?
So I haven't even given you any invariants yet. So all of these things are not known very well. So I'll come to this on the next slides, but it's not like we have a huge number of trisection invariants so far. And as in knot theory, like it depends a lot on the data you put. But I think this is not fine, has not gone far enough to really address these questions. So now the task is not to have a more elaborate trisection invariant, but to have any trisection invariant at all that is not completely trivial. And this was done in 2019 by Scheides, Kotler, and Pull. And in the following, I just called it CCC. And the idea they had is basically we know Heegard diagrams, and from Heegard diagrams we can construct a Kuperberg invariant. That is done by assigning a Hopf algebra. Each color, so for the red curves you take one Hopf algebra, for the blue curves you take the dual Hopf algebra, and then you apply some sort of algorithm and it gives you a 3-manifold invariant. And they had the idea that one could try to do something similar for the trisection for the trisection diagrams, and they did it in fact. So the question is then, what is the algebraic data? And the algebraic data they put is what they call a Hopf triplet. So here I present it in the simplest possible version. So I don't want to worry about anything. So I say the field is C. This can be done in more generality, but it's easiest over C. And the Hopf algebras should be finite dimensional and semi-simple. And here I've already drawn them in color. So one Hopf algebra belongs to the red curves, one Hopf algebra to the blue curves, and one to the green curves, always in the color in which they're written, and also in the color of their letters. So C is for green, that's an approximation. Okay, so one takes these finite dimensional semi-simple Hopf algebras and one needs some additional structure. So the first bit of additional structure that I need is something that is called skew pairings in the textbook literature. That's essentially a linear form on the tensor product of two of these Hopf algebras, always one Hopf algebra and the next one, that satisfies certain compatibility condition with their multiplication and co-multiplication. And here I've chosen to write this in a slightly different way. So here I take these skew pairings as elements of the tensor products of the dual Hopf algebras. And then this compatibility condition becomes something that seems familiar from the R matrices. So this is a condition that is also satisfied by universal R matrices. And here this condition is also similar. But it's not required that the skew pairings are non-degenerate. You can see this as a generalization of an R matrix, in fact. So if you have a co-quasi-triangular Hopf algebra where the dual is quasi-triangular, then you can take the R matrix of the dual to define such a skew pairing. And then these conditions here are just the familiar condition for the universal R matrix. So this is kind of one example that one can take. Okay, and then what I also need is a further compatibility condition between the three different skew pairings. And if one thinks already in the direction of R matrices, then one can see this further compatibility condition as a sort of quantum Yang-Baxter equation. Just that it lives not in one Hopf algebra, but it lives in three different Hopf algebras. Okay, so that's the algebraic structure used by
our matrix also satisfies some conjugation. Yeah, there's a conjugation equation between the.
This is not true here. I mean, this makes no sense.
Not yeah.
So it's like a generalization of those properties of the R matrix that you can reasonably generate. However, yeah. It's so if you think in terms of Hopf algebras, it defines your twist. And the R matrix can also, this can also define your twist. Then you get the Drinfeld double, but it doesn't satisfy any compatibility condition like you proposed. Okay, so that's the algebraic data. And then they defined the four-manifold invariant as follows. So they define something they call a trisection bracket of a trisection diagram that's exactly analogous to the construction of the Cooper-Berg invariant. So what I do is first you choose an orientation and a base point for all of the curves in the diagram. And then you associate to the red curve the integral of the red Hopf algebra. So here I'm talking about a normalized two-sided integral. And to the blue curve, the integral of the blue Hopf algebra, and to the green curve, the integral of the green Hopf algebra. Then for each curve, you apply the co-multiplication. So if you have a curve that has n intersection points with curves in different color, you apply an n-1 fold coproduct. So instead of one copy of the Hopf algebra, you now have more. And this n-1, the n-1 fold coproduct of this integral that is assigned to the curve is then associated to the different intersection points. So I start here at the base point, and then the first intersection point gets the first copy, second intersection point the second, and so on. And if you do this to all the curves, you get some element of some big tensor product of the Hopf algebras A, B, and C where each of the Hopf algebra comes up as often as you have intersection points with curves of that color. The next step is that you apply these Q pairings and you take into account the signs. So for each intersection point, you have like two copies in this big tensor product that belong to the intersection point, and they're of different colors. So you can kind of move them next to each other. And then you apply this Q pairing, where you apply this Q pairing if it has a positive intersection sign. So these are these three here. And if there's a negative intersection sign, that are the other three, then you apply the inverse of this Q pairing. And this gives you a number. And this number is not quite a trisection invariant. So it's true for this number that the invertibility of these Q pairings gives you the Reidemeister 2 move. This condition here gives you invariant under the 3-point moves. And invariance under the Handel slides you get essentially from the properties of these two-sided integrals. But there's one more step to really get a 4-manifold invariant. And that has to do with the stabilization and destabilization move. So for this one needs an additional condition. And the condition is that if one evaluates the trisection bracket of the stabilization surface, so S4, that this is non-zero. And then you have a complex number, an invertible complex number, whose third power is equal to this trisection bracket. And then you use that to rescale. So you rescale the trisection bracket with this number to the power minus genus of the trisection diagram. This is a bit similar to the Kaufmann bracket, for example, in knot theory. Yeah, and then they have shown that the resulting map that assigns to each trisection diagram this kind of rescaled trisection bracket here, that this number is really a trisection invariant. Yes?
So, sorry, I didn't follow. We had like an element of triplet, and then how did we get the number from it?
Okay, I'll say it again. So here we assign to each curve, we assign an integral. And then we use the co-multiplication to make out of this one copy, the one integral, we apply an n-1-fold co-multiplication, and we assign it to the intersection points on the curve in the order in which they come up.
Right.
And then we kind of pair the two such copies. We pair them for each intersection point by this Q pairing.
Question. Almost looks like if A was quasi-triangular and you set A, so quasi-triangular and you set A equals B equals C, that we get a simple structure. Is that true?
If you say A is co-quasi-triangular and you say A equals B equals C, you would get such a structure. It's not the only thing you can do, but this would work.
Not completely trivial. That's
So I haven't looked at this specific case, but there are some similar examples where you also take one co-quasi-triangular and it's not completely trivial. I come to this.
Sorry, I have one more question. So when you say it generalizes Kuperberg's invariance for 3 manifolds,
Yeah.
this is for 4 manifolds.
So what I mean by generalize is the procedure that one does here. This procedure is almost literally just what you do for Kuperberg invariance. So this is some very well-known thing, and the only thing you are changing is changing a bit of algebraic data.
It would be like more precise if you take the manifold and cross it with S1 and compute this invariant. That doesn't.
So you want to use it for 3 manifold times S1?
Yes, and then like computing this invariant and then seeing Kuperberg at the first factor.
So I think this would not be just the Kuperberg invariant times something. So this you could compute it for that case, but I don't think.
Choosing the right trisection diagrams, right? Of course, for the problem. That's.
I mean, so I cannot compute it in my head, but if there are some examples in the literature where you do these diagrams for product manifolds and they're not so simple. But I don't think it just gives the Kuperberg invariant times something. Okay, but I'll give you some examples for this.
And one more.
Yeah.
And at which point did we use semi-simple now?
For the existence of the two-sided normalized integral.
Okay.
And we need that. I mean, I haven't shown where it enters the proof, but you need that. And we have also needed it for antipode square is equal to the identity. I mean, of course, this you could impose separately and work over a different field, but you will just get problems because then you need to find the third root of this number and so on. But it really enters. It's like with the Cooper-Berg invariance, you can do it in a different setting, but then you have to work. Okay, so I'll give some examples now. One easy example, what you could do is you take just some Hopf algebra A and you take that C is the dual of B. Then you have a canonical skew pairing between B and C, just the evaluation. And to make a skew pairing with A and B and with A and C, you need some Hopf algebra map from the Drinfeld double of B to A. And this gives you these skew pairings. So this is an example that by CCC, and one can show that in this situation, one gets a different four-manifold invariant, namely the one by Behrens and Barrett, for the situation where Behrens and Barrett is taken for the center of the representation category B mod, and where one has the functor is induced by this Hopf algebra map. So you have a functor from A mod to the center of B mod. So this is a known four-manifold invariant, and it shows to some degree that this is not something trivial. Because the Behrens-Barrett invariant has a special cases, the Cranietta invariant, the refined Broda invariant, and Petit's dichromatic invariant. So this is not a statement that under all circumstances this will coincide with the Behrens-Barrett invariant, but at least in this situation one gets it.
Sorry. Did the Cranietta follow from the example where all the Hopf algebras are the same?
So one would guess that the Cranietta would follow from the example where you take, where two of the Hopf algebras are the same, or like one is the dual of the other, and the third one is the dual of the Drinfeld double of the first. So you take B and B star, and you take the dual of the Drinfeld double of B. That's my guess. And that's also what comes out from the Behrens-Barrett so the invariant, because what you can do then is here already you have a center. And the easiest thing you could do for this functor from A mod to the center of B mod is simply to say that this functor is the identity. That's okay. And then there's one other case that was investigated in more detail there, and that's a conjecture from the paper CCC. So here one takes for A the algebra of functions, the complex functions on Zn. For C, one takes also the algebra of complex functions on Zn. And for B, one takes the group algebra of Zn. And then one has easy skew pairings between AB and BC. That's just the duality between the algebra of functions and the group algebra. And then, what one suggested before, one can say, okay, we need still a pairing between C and A. There we can just take a very well-known R matrix for the group algebra of Zn. And there are many examples they computed. They have a conjecture that this is Kashaev's invariant. That is important. We have a lot of examples, but it's still a conjecture, so they could not prove it. So it's a pretty good invariant, and I think it's worth looking at, and it's interesting. But the starting point for our work were the following questions. So somehow this Hopf triplet is a structure one has never seen before. It's a bit artificial. One doesn't know any other part of mathematics where this plays a role. Then also, if one already kind of takes the Cooper-Berg invariance as a guidance, then one should also note that for Cooper-Berg invariants, at least in those cases where everything is nice, they're related to Taurav-Viro invariants. So you would expect there should be a tensor categorical or spherical fusion categorical counterpart of this construction, and it's not known. And the third observation is that everything in the trisection diagrams is by definition very diagrammatic. So one could guess that some diagrammatic calculi that were developed for fusion categories, bimodule categories, and so on could be helpful in this setting. So that were our questions. Okay, so that's what we try to do. So we try to give a categorical counterpart or generalization of this construction. Okay, so how can one think about what could be the right structure? So instead of the two Hopf algebras B and C, one would maybe take some special conclusion categories. And what we then took is a finite semi-simple indecomposable bimodule category that is equipped with a bimodule trace. So this notion of a bimodule trace is to Schumann. And was already quite useful in a lot of work. So why do we want to take this data? Because it makes these three colors somehow natural. So if we have two spherical fusion categories and we have a bimodule category over them that has the appropriate properties, then we get a new spherical fusion category, namely the spherical fusion category of bimodule endofunctors between them and bimodule natural transformations. And this finite semi-simple is for convenience and also because we need it. And the indecomposable is that this is indeed a spherical fusion category and not just a multi-fusion category. So here it's somehow very natural that we have three colors and we do not have to put in a construction, but something that is already there. And one also has some idea here what one would put on the crossings. So the crossings before had these Q pairings. Now one can think, if one has this data, there are like three coherence isomorphisms that mix the different colors. So here we say the B belongs to the blue curves, the C belongs to the green curves, and the A belongs to the red curves. So what do we put on the crossings? On the crossings, we put simply these three coherence isomorphisms that we have that relate these colors. So if you have a red and green crossing, then the red is labeled by a bimodule endofunctor, the green is labeled by some object of the spherical fusion category C. So what we put here is the coherence isomorphism that tells me it doesn't matter if I first act and then apply the bimodule functor, or if I first apply the functor and then act. Similarly, for the blue curves and for the intersections of the red and blue, there the action is now from the right. And I put the coherence isomorphism that tells me it doesn't matter if I first act and then apply the functor or the other way around. And finally, if we have a blue-green crossing, well, that's the coherence isomorphism for the bimodule category. So it doesn't matter if I first act on the left or if I first act on the right. There are, of course, more coherence isomorphisms, but the other coherence isomorphisms are essentially invisible in the diagrammatic calculus. And if one looks at these coherence isomorphisms, one will see that indeed here one has something like a colored Reidemeister 3 relation. That's largely, so the well-definedness of this diagram comes from some other coherence isomorphisms that are invisible. And the fact that one has Reidemeister 3 is because of the naturality. So here one would say it's not so strange at all that one has these three different colors, and also one doesn't put anything artificial on the crossings because one just puts what one has already in the setting. So that was our starting point. And then the idea is to use diagrammatic calculus to just evaluate some trisection diagram. So I need to speak a little bit about diagrammatic calculus. So this is from some older work that had a different purpose. And I will just present what is necessary for here. So I will not present this in full generality. So what we have is some oriented surface, possibly with a boundary. And we have red and blue and green curves on the surface that we label by
It's not real. It's just a test.
So it will just stop on its own.
Stop it.
It's 1 minute too early.
Maybe then it's real.
Okay. So we consider an oriented surface, possibly with a boundary, and we have red, blue, and green curves on the surface. Now the curves are oriented as indicated by these arrows, and they're labeled with objects of A, B, and C. And when the curves come up to the boundary, they can end there. So we have certain boundary segments, and we have endpoints at the boundary. And we label these segments by some object of this bimodule category M, and we label the curve endpoints at the boundary by appropriate morphism spaces. And which one you have to take, you see from the labels of the objects on the segments before and after, and also from the fact if this line is incoming or outgoing. Okay, and then this calculus works as follows. So first you cut the surface into disks, maybe one disk, maybe several ones, as you like. And to the crossings on the surface, you associate these coherence isomorphisms that I have drawn here, or you put the inverses if the crossings have the opposite sign. Out of this, you get such a labeled disk, also with like objects and morphisms at the boundary of the disks and some crossings going on in the interior. And this disk can be evaluated to a trace of a certain endomorphism of the bimodule category. And then in the end, you have some identities to glue disks by summing over dual bases of morphism spaces, like the ones that are sitting here, and over the simple objects in the bimodule category. So these segments are then summed over the simple objects. And I want to illustrate this with an example. So here we have such a disk with curves and crossings and some labels at the boundary. What you do then is you can cut open the disk somewhere, maybe not at the end point of a line, and then you straighten the disk to a line. So I just cut it open and bend it vertically. And then you get something like a linear chord diagram, where the segments are again labeled by objects of this bimodule category. The chords are labeled, they inherit the labeling from here. So they're labeled with objects of A, B, and C. And at these points here, you have certain morphisms. And this diagram you can evaluate. So in a very simple way. So here you start out with M. So you put the object M. Then you have a morphism alpha. So you apply the morphism alpha. And then you go to f of n. So here you have the object n, but you have a functor to the left of it. So you apply the functor. And here you don't apply beta because you have the f to the left of it, you apply f of beta. And similar, you go down from the top to the bottom of this chord and just apply all the functors that are on the left to the things that are on the vertical line. And then you will notice that at some point you have to apply the coherence isomorphism to continue doing that. That's here, here, and here. That corresponds to these crossing points. And if you apply them correctly, you get an endomorphism of this object that is at the top and at the bottom of the diagram. So it's an endomorphism. And then you take the trace of this and call this the evaluation of the disk. Okay, that's the first step. So now you can evaluate a disk. And then there are some cutting and gluing identities that allow you to glue them. So if you have here two disks, they're shaded. And then you have a line that comes up here. And this line continues here, and here you have the same labels. Then you can fuse these diagrams by summing over dual bases here of these morphism spaces associated with the line endpoint. And then you just fuse the two disks to one. And similarly, you have a type of, like a Pac-Man. Here you have like a part of a disk. Then here you have a line. Here you have a line, and here you have like some object sitting there. You can kind of close this gap here by summing over the dual bases of the morphism spaces and also summing over the simple objects associated to here and multiplying by their dimensions. And then this gap here just closes and you get this picture. So yeah. And in this older work, I've shown that this evaluation is independent of all the things that you're choosing here, like the basis of the Hom spaces, the choices of representatives of the simple objects, for example, here, sum over representatives, And also, and this is of course the most difficult, to show that it doesn't depend on how you cut the surface. So in principle, this formalism gives one a way to evaluate such a trisection surface. Up to two minor details. The first one is here we need to label the curves, and in the trisection surface they're not labeled. And the second one is that the curves here are oriented in the trisection. So what one can do now, simply if one doesn't want to put labels, one just puts all labels. One sums over the simple labels. This way one can just apply it. And one should also make use of a little bit of freedom one has. One can in principle also consider not the three categories that we have here, but three new spherical fusion categories and equip them with pivotal factors. So one has a bit more freedom. And we use this freedom partially. Today we have three spherical fusion categories A, B, and C. We say that M is an indecomposable bimodule category for the second two fusion categories with the bimodule trace, and that we have a pivotal functor that goes from the first spherical fusion category to the category of bimodule endofunctors and endonatural transformations. So pivotal means it respects the units. Okay. It respects the pivotal structure, and that implies that it respects the traces. Okay, so this is what we need. And then we just define the averaged evaluation of a trisection diagram as the sum over all labelings here of red curves with objects of A, blue curves of objects with B, and green curves of objects with C. And then we multiply with the dimensions of all the labels, and then we just evaluate the labeled diagram. So this is something that we can do, and it gives for each trisection diagram a number. Okay. And what we have shown now is under the condition that this averaged evaluation of the stabilization surface with the disk removed. So here we remove a disk and we label it with an object M. If the average evaluation of this is non-zero for all the simple objects, then one can show there is a complex number, an invertible complex number, such that this averaged evaluation is just the dimension of the boundary label times the third power of this number. That's the equivalent or the counterpart of the condition that was also in the Hopf algebraic version. Yes, and then we have shown that this indeed defines a trisection invariant. So it's invariant under all the moves that one has. And as in the Hopf algebraic version, here we need to rescale with this complex number. Then the question is, okay, if we have this, so how is it related to the Hopf algebraic version? Is it something alternative? Is the former a special case of the latter? Are they only related in some cases?
Sorry, can I ask a question? What's the dimension of M? M is an object in this bimodule category, right?
It's the trace of the identity morphism on M. We have a bimodule trace.
Oh, okay.
Sorry, I should have said this. So
No,
that
you just said it. Yeah, it's written.
Okay.
Yeah.
Yeah. Okay. Further questions? Okay. So how is it related to the trisection invariance in the Hopf algebraic version? So the statement is these Hopf algebraic trisection invariants from CCC are the same as our trisection invariants in the case where this bimodule category is just the category of vector space, finite dimensional vector spaces. And this goes in both directions. So the claim is that if we have a Hopf triplet, or if we have the assumptions that are needed for and the data needed for CCC, then we can build from this data bimodule categories. We can build from this data the required spherical fusion categories. We get a bimodule category structure on vect, and we also get such a pivotal functor as here. And in the other direction, if we take our formalism and for the case where M is the category of finite dimensional vector spaces, then we get the Hopf triplet as needed by CCC, and we get these Q pairings. Okay, I want to say a little bit about how to prove this. So about the first theorem that we get a trisection invariant is not so difficult. because the first three moves are already built in the diagrammatic calculus. So if I apply a diffeomorphism to the surface, then basically nothing changes because all these curves are carried with it. And this is very simple. The 2-point move and the 3-point move are also built into the diagrammatic calculus. So this here is the invertibility of the coherence isomorphisms. And this here is like the naturality of the coherence isomorphisms. So there's not much to do here. And for the Handel slides, it's also not so difficult because there's a spherical fusion category. Well, in a spherical fusion category, we can work with like something like the Kirby color. It's often called the Kirby color. We just take the sum over all the simple over a set of representatives of the simple object and multiply with the dimensions and take the objects. So this is the counterpart of all these two-sided integrals in the Hopf algebra case. And by a fairly standard diagrammatic computation, one can then show that in slides. The last point is the most difficult. So for the destabilization, one really needs an idea, and one really needs everything that we have so far. So we need the gluing identities, we need the Handel slides, and we need the bimodule trace. So what we're doing essentially is we're punching a small hole here. So we remove a disk, and then we surround this hole with the blue and the green curve. And then we slide the blue and the green curves over like the other curves that are there with the Handel slide identity. And on the other hand, we know that this defines a bimodule trace. And in this way, we can compare and we get the statement that it doesn't depend on the boundary label. But this is not so easy. But it's all really properties that are very intrinsic either to spherical fusion categories or to the diagrammatic calculus. For the second theorem, yes, so if we have a Hopf triplet in the sense of CCC, we just define our spherical fusion categories as the modules over the dual Hopf algebras, up to some ops and cops, which I will not comment because they're complicated. And we take as M category of finite dimensional vector spaces. And the skew pairings then define a bimodule category structure on vec. So the BC skew pairing gives us the bimodule category structure, and the AB and the CA pairing define this pivotal functor. So they define the coherence isomorphisms, but also the functor. And in the other direction, it's simply with fiber functors. So if we have a bimodule category structure on vect, this is the same as having a fiber functor. And this fiber functor gives me Hopf algebras. So this fiber functor here tells me that C tensor B, C the linear Bref is some representation category of a tensor product of two Hopf algebras. And one can then show that the module endofunctors are also representation category of a Hopf algebra, which is sometimes called the double of B and C. It's like a generalized double. Yes, and then in the end, the pivotal functor that you put into the formalism then gives you a fiber functor for the third of the categories that we have used, and then one can really see its equivalent. Okay. So in some sense, this gives a generalization of CCC, and it's really a non-trivial generalization because it covers more data. But this raises also some questions, namely what happens if I do not have these fiber functors? So if I have simply spherical fusion categories that are not representation categories of Hopf algebras, and also what is the role of this bimodule category when it's not vect? And this was already considered by CCC as a question what they can do with their formalism to generalize it, and they had some idea that probably this would involve weak Hopf algebras, but they didn't really state it. And one can see in a simple example that this really works and how it works for the other situation where we don't have these fiber functors. And the non-existence of the fiber functor is not the fault of the spherical fusion categories, it's really the fault of the non-triviality of the bimodule category. So here we have a very simple example. So we take digraph-Witten theory, So we take for B, the B-graded vector spaces, where B is a finite group. For C, we take the C-graded vector spaces, where C is a finite group. For the bimodule category, we take the vector spaces graded by a finite set with an action of the two groups, a left action of C and a right action of B. And then we take A is the category of bimodule n of factors of that. So that's a very simple example. And what we could show with this example is the following. In this case, we need to take a generalization of what CCC were doing. It's a generalization, and the generalization uses a V-Kopf triplet. So we had this definition of the V-Kopf triplet. If we go back, then we will see it involved these Q pairings. This can also be done for V-Kopf algebra. There's no problem with that. And also for these identities that we have, there's no problem in case of a V-Kopf algebra. And for the generalized Young-Baxter equation, there's also not a generalized quantum Young-Baxter equation, there's also no problem. So there's a very obvious way to generalize what CCC were doing to V-Kopf algebras. And if you do our formalism for Dijkgraaf-Witten, then you will get exactly that. So I should say, what is the V-Kopf triplet? It takes a simple form. So it's always made up of algebras of functions. So here we have the algebra of functions on C times B op. And here we have the free vector spaces generated by M times M. Here we have the algebra of functions on M times M. And we have some group algebra. Here similarly, we have the algebra of functions on M times M. And we have some other group algebra. And one sees, if one looks at this, that the B tilde and the C tilde, they're contained in the dual here of the A tilde. Okay, then we need to talk about skew pairings. Well, as these here are contained in the dual of the other, we can just take the canonical duality pairing between A and A tilde. A tilde and A tilde star. So this is just V-Kopf algebra duality. And the other one is more tricky. This one needs to really find. And this pairing is written like here. So the group elements B and C here play no role. The only thing that plays a role are these functions on M times M. And what one essentially takes is delta functions in a controlled way. I'll explain later why. So this works. And one can even compute what one gets in this situation. So what one gets from our invariant is it's the number of admissible labelings of the trisection diagram rescaled with the number of admissible labelings of the standard trisection diagram for the S4. Okay, so what are admissible labelings? Admissible labeling means that I associate to all the regions in the diagram between the curves some elements of M. To the blue curves, I associate elements of B. To the green curves, elements of C. And then it must satisfy two conditions. So for each red curve, the ordered and signed product of the elements of B and C associated to the curves that intersect it must be equal to 1. So the red curves cut the green and the blue. And for all the blue and the green curves, the labels in the regions to the left and the right of the curve must be related by the action. Yeah. And that's essentially what comes out and what is the result. Now can one understand somehow the role of these V-Kopf algebras and its relation to the diagrammatic calculus? And the statement is this. So essentially these V-Kopf algebras are just the diagrammatic calculus. So we can visualize the Hopf algebra element of the V-Kopf algebra A tilde, we can visualize them. So this is a general element here. We can visualize them by a red line, where we put this element here, we put at the tip of the arrow, and the elements in M times N we put to the left and to the right. And then one would say to the starting point here, one just puts the ones that are obtained from N and M by acting with this K. So here K is the product of the groups C and B op. So this is what one can do to visualize, and similarly for the dual Hopf algebra with like one difference, we put still this element of the group algebra here, we put on the tip of the arrow, but the two labels that we get from here, these delta functions here, these we put to the left, one at the start and one of the target. And then we would say on the right, we have just the ones that are obtained by acting. And now one can write down all the Hopf algebra structures, the multiplication and the co-multiplication. Then we also need the integrals. We would maybe need the units, but that are left out for space reasons. And then also the skew pairing. So what does one see from these formulas? And look at this formula here. If one wants to multiply two such Hopf algebra elements, here the labels on the tip of the arrow must match for a tilde, and also the labels in the region between must match. That's the two deltas. And similarly in the other Hopf algebra, in the dual, here we just multiply the labels at the tip of the arrow, and we impose that the label here must be the same as the one on the right here. So the multiplication is just matching of the labels in the regions and doing something very obvious with the tip of the arrow. And similarly for the co-multiplications, there's a similar procedure, and also the integrals we can write down nicely. And then one sees, if one looks at the skew pairings, so here I've taken a skew pairing of a tilde with either blue or green. And what happens here, if one looks at this, is one forces here these group elements at the tips of the arrow to be equal. And one says the labels in the regions between the arrows must match. So we must have that the P is equal to the M, and we have that the N. So basically this is just consistency of the diagrammatic calculus. And similarly, if we have a green and a blue crossing, so here it makes no sense whatsoever to make the group elements match because they're from different groups. So just nothing happens with these elements, they don't see each other, but we have various consistency conditions here for the labels. So these two must be equal. That's the first one here. Then this must be equal to the one obtained by acting with the C on that. So we pull it through basically, that's this. And then we have another condition that relates this one and this one. So indeed we get weak Hopf algebras as the CCC anticipated. And the diagrammatic calculus is in principle just the structure of the weak Hopf algebras. Okay. So I summarize. So we can generalize these Hopf algebraic, a bit maybe ad hoc invariants from CCC to categorical versions, and that these categorical versions are somehow very natural because we just take spherical fusion categories, a bimodule category, with appropriate properties, and then we get for free another spherical fusion category. So it's natural that there are three colors. And the trisection diagrams are just a special case of some diagrammatic calculus that exists already. Okay, then there are many questions. So what we do not know, so like all the things I presented are really proved. So this is not hope, or they're all proved. It's just not fully written up yet. But there are some open questions, and open questions were already raised. Like one is about the power of these trisection invariants. Like which four manifolds can you distinguish with them? And is it also that like categorical ones are truly better than the Hopf algebraic ones? Does this give you some new insights? And I would say this is a fairly difficult thing to address because the trisection diagrams themselves are very hard. So they're very hard to write down, and it's also not obvious how to evaluate them in practice. So very soon I would maybe wish for some computer program to do this. So this is a really unclear question. And another question that comes up is what is the relation to four-dimensional TQFT? So is this just some weird description of a four-dimensional TQFT or not? And the answer to this is also we do not know. And I can explain why we do not know. So first, if I want to compare it to a four-dimensional TQFT, I need to somehow write this down. One obvious thing would to use TQFTs that are defined by triangulations. But what is true in 3 dimensions that you get a Hegat splitting from a triangulation is not true in 4 dimensions. You do not just get a trisection from a triangulation. There is a procedure of getting trisections from tricolored triangulations. So this is triangulations where the vertices have the colors red, blue, and green, and every 4 simplex has all 3 colors. But the colors are really important here. And so it's not very obvious. And in this way, you can make trisection invariants, but then when you try to glue, you can glue triangulations. Something weird happens to these bits of surface. So then you have bits of surface sitting in these triangulations. And when you glue them, you do not glue them in the usual way. Like in TQFT, you would imagine in the 2-dimensional case, you're just gluing like these circles at the ends, but there you're gluing like different bits of the surface, like several bits around a point, not just one circle with one circle, but like several different arms come out of such a gluing point. So this is not obvious. The other thing that is not obvious is one could also now say, okay, maybe the triangulations are not the best idea. Let's just kind of generalize the trisections to manifolds with boundaries. And in the paper by Gay and Kirby, this also has been done. So there is a kind of boundary counterpart of works with compression bodies. This is fairly natural from their focus to define it like they define it, because they're interested in these Morse 2 functions. But I'm not so sure if this is the right thing for the TQFT picture, because it's stated explicitly in their paper that you can consider manifolds with boundaries, but if you glue 2 trisections with boundaries, you do not necessarily get a new trisection. So somehow this tells you it's not so easy to relate it directly to a TQFT. Of course, it could still be related to a TQFT, but simply we don't know at this point. But still, I think it's a fairly interesting approach to 4 manifolds, and I think it's intriguing also that you can use such simple 2-dimensional diagrams. This diagram comes in such a natural way. Okay, thank you for your attention.